Welcome to this special report from the Deep Dive. Today, we are tracking a celestial body that serves as both a guest and, well, a profound scientific challenge.
It's an object that originated far, far beyond the reach of our sun's gravitational influence.
We are reporting on 3I Atlas, and this is only the third known interstellar object to have ever entered our solar system.
That's right. And its sheer velocity, its trajectory, it immediately told astronomers this was something foreign. And its transit has triggered what I think can only be described as an unprecedented, system-wide, coordinated observation campaign by NASA.
And that coordination, that's really the core of this story, isn't it? This wasn't a scramble.
No, not at all.
It was a strategically executed deep dive, and it involved 12 distinct NASA assets.
12. Think about that. These are resources spread across the entire solar system.
We're talking orbital platforms circling Mars, deep space explorers on their way out to Jupiter's asteroids.
And their collective focus was absolutely singular. It was to understand how this interstellar visitor is different, chemically and structurally, from the materials that formed our own sun, our planets, and of course, our native comets.
So the scientific prize here is huge.
Well, it's nothing less than a new direct window into the composition of other star systems. For the first time, we're able to take an almost immediate comparison.
A side-by-side.
Exactly. A side-by-side of the fundamental building blocks of our galactic neighborhood versus those that were forged in a solar nebula light years away. It's tangible exoplanetary science, but without ever having to leave home.
The discovery itself actually happened pretty recently, July 1st of this year.
That's right. It was first spotted by the NASA-funded ATLS telescope.
That's the Asteroid Terrestrial Impact Last Alert System.
The very one operating down in Chile. And right from the very start, its speed was the defining characteristic.
What kind of speed are we talking about?
Well, the reported speed is around 130,000 miles per hour. That's about 209,000 kilometers per hour. And that speed, it places it firmly on what we call a hyperbolic trajectory. It's just too fast to be gravitationally captured by the sun.
So it's not sticking around.
Not a chance. It's a true cosmic transient. You can think of it as a piece of matter that was ejected from its home star system, and now it's just slingshotting through our cosmic backyard on its way back into the interstellar void.
Over the course of this report, we're going to walk you through the precise details of this astronomical interception campaign. We'll start with the critical close-up observations that were captured in what we're calling the Mars Reconnaissance Zone.
That's where scientists got their most detailed, most intimate look at the object.
Then we'll pivot to the Solar Exclusion Zone, a period where specialized solar observing missions had to take over tracking when Earth was essentially blinded by the sun's glare.
A huge challenge.
And finally, we'll examine the contributions of these deep space probes that were repurposed mid-journey to provide these unique, high-angle views of this fast-moving comet.
Our mission today is really to unpack the specifics. The data gathered at each of these strategic vantage points, and crucially, to assess what the immediate scientific implications are. What do these findings mean for our understanding of how planetary systems are born across the galaxy?
Okay, so let's begin where the data was most tightly focused. That would be 3I Atlas's closest approach to a planetary body observed by NASA, which was its flyby of Mars.
Right. Earlier this fall, the comet passed the red planet at a distance of about 19 million miles.
19 million miles. That sounds incredibly far, but in cosmic terms, that's practically next door for this kind of observation.
It is. That 19 million mile proximity, or roughly 30 million kilometers, it was a golden window for observation. It placed the comet perfectly within the operational reach of 3 separate NASA assets that were already there, already dedicated to Mars science.
So you had the Mars Reconnaissance Orbiter, MRO.
The MAVEN orbiter.
And I found this surprising, the Perseverance rover actually operating on the surface.
A real bonus observation, that one.
Let's start with the visual capture. The one from the Mars Reconnaissance Orbiter, MRO. Its camera, the high-resolution imaging science experiment HiRISE, it's arguably one of the most powerful cameras ever sent to deep space.
It's an incredible piece of hardware, and it captured an image of 3I Atlas on October 2nd, 2025.
I have to imagine the feat required to get that single image is something we can't overstate.
You really can't. When that photo was taken, the comet was 0.2 astronomical units away from the spacecraft. Now, HiRISE is designed primarily to photograph stationary features on the Martian surface.
Craters, dunes, ancient riverbeds, things that don't move.
Exactly, with incredible precision, but they don't move. So its targeting system had to be completely repurposed on the fly to track an extremely faint, rapidly moving target across a vast distance.
I really want to understand the mechanics of that. You have a moving spacecraft trying to image a moving comet from 19 million miles away. How challenging is that?
It's a profound engineering challenge, and it all comes down to predictive modeling. You see, HiRISE has an extremely narrow field of view.
Like looking through a drinking straw.
A very, very long drinking straw. So even the slightest error in predicting where 3I Tellus would be at that exact moment would result in a completely missed shot. Just empty space.
And you can't just take a long exposure, I assume, because everything's moving.
That's the other problem. Because the comet is moving at that high hyperbolic speed, a long exposure would just be a blurry streak. So they had to execute these rapid high-gain captures and then stack them later in processing, all while compensating for the relative motion of MRO itself, of Mars, and of the comet.
So the success of that October 2nd image wasn't just about getting a pretty picture.
Not at all. It was about confirming the precise astrometry, the exact position and path, which was needed for every single subsequent observation by every other instrument. It set the stage.
Okay, so moving from high-resolution imagery to the chemistry, this is where, for me, the truly fascinating data came from. We're talking about the MAVEN orbiter.
Yes, MAVEN, the Mars Atmosphere and Volatile Evolution spacecraft. It obtained ultraviolet images on September 28th, so just a few days before that closest approach.
And MAVEN used its imaging ultraviolet spectrograph, or IUVS.
Right. And unlike MRO, MAVEN's goal isn't surface detail, it's all about atmospheric analysis. By looking in the UV spectrum, the IUVS can identify specific volatile compounds, gases that are sublimating or boiling off the comet's nucleus.
It's essentially providing a taste of its composition.
That's a perfect way to put it.
So the primary focus was hydrogen. But hydrogen is, well, it's the most common element in the universe. It's everywhere.
Exactly, and that was the challenge. MAVEN had to contend with hydrogen from the comet, hydrogen from the Martian atmosphere, and the background hydrogen that's just flowing through the interplanetary medium, from the solar wind.
So how did they possibly separate these three distinct yet chemically identical sources?
That is the technological masterpiece of this particular capture. They didn't rely on location or just light intensity. MAV used a special operational mode to separate these sources based entirely on their speed relative to the spacecraft.
And they did this using the Doppler shift.
The Doppler shift, yes.
So for our listeners, let's just quickly unpack that. It's the same reason an ambulance siren changes pitch as it drives past you, right?
It's the exact same principle. When an object that's emitting light is moving rapidly toward you, the observer, the light waves, get compressed. They shift slightly toward the blue end of the spectrum.
And if it's moving away?
The waves are stretched and they shift toward the red end. That's the Doppler effect. So in MAVEN's case, because the Martian hydrogen is moving at one velocity, the interplanetary solar wind hydrogen is at another. And the hydrogen from 3I Atlas, traveling at that incredible 130,000 miles per hour, is moving at a wildly different, highly redshifted velocity.
So ambient spectrograph could literally filter the UV light based on those tiny spectral shifts. It could tell them apart by their speed.
Precisely. They weren't just seeing a big cloud of hydrogen. They were seeing three distinct velocity signatures that corresponded to three completely different origins. That's how they isolated the emissions originating only from 3I Atlas.
That's incredible. So what does isolating that specific hydrogen emission tell us about the comet itself?
Well, the key finding visually was that the comet's hydrogen cloud, its coma, appeared to be tightly confined and relatively small. And that's especially interesting given how close it was to the sun and the weight of sublimation you'd expect from a standard solar system comet.
What does that suggest?
It suggests a few critical possibilities. First, the ices in 3A Atlas might be less water-rich than our typical long-period comets. Or perhaps those ices are buried deeper under a protective, less volatile crust.
Interesting. So if it's less active than expected, it could mean this interstellar object has either spent a very, very long time in the cold void of space, which allowed a thick crust to form.
Or its internal composition is just richer and heavier, less easily sublimated molecules.
Did MAVEN look for anything besides hydrogen?
Oh, absolutely. They targeted other volatiles. They were searching for signatures of carbon-based molecules, things like carbon monoxide, CO, or carbon dioxide, CO2, and potentially oxygen emissions as well.
And why are those specific ones so important?
Because if the comet showed a high proportion of CO or CO2 relative to water, which we can infer from that hydrogen cloud, It would be a very strong indicator that 3-Ditilas formed in a region of its home star system that was significantly colder than the region where our own solar system's comets formed.
So the immediate implication here is a clue about the temperature gradient of the protoplanetary disk where this comet was actually born.
Exactly. I mean, this clean, Doppler-shifted sample, it provides this essential baseline data, completely free from contamination, that tells us about the interstellar composition before solar heating has a chance to severely alter it. It's a pristine sample.
So we had the orbiters providing this high-ground strategic view, but then we have the ground report from the Perseverance rover. While the orbiters were doing their work, Perseverance still managed to grab a faint glimpse from the rim of Mars's Jezero crater on October 4th.
And this really was a bonus observation. It wasn't a primary goal, but they took the opportunity. Perseverance used its Mastcam-Z, which is a high-definition camera system. At the time, the comet was still 18.6 million miles away.
Trying to image something that far away from the surface of a planet, looking up through an atmosphere, it must have been incredibly difficult.
It's akin to trying to spot a single candle flame that's been lit on the opposite side of a continent. You need perfect timing and basically zero atmospheric disturbance.
So it must have been incredibly faint in the final image. Just a smudge.
Faint is an understatement. It was right at the limits of detection. It appeared as just a slight, blurred streak against the background star field in the final composite image.
So what's the scientific value of a single faint smudge?
Its value lies in providing an observation baseline from the surface. You're seeing the comet's visual brightness as it's filtered through a planetary atmosphere. And that allowed researchers to calibrate and cross-reference the brightness data that was being captured at the same time by the orbiting spacecraft. It helps tie all the data sets together.
So to sum up this first part, the Mars Reconnaissance Zone delivered the most chemically detailed and geographically close-up view of 3-I's. It provided the foundational data points for the entire rest of the campaign.
That's right. But as the comet dipped closer to the sun, the tracking baton had to be passed. The data capture at Mars was complete, precise, and highly coordinated, but the object was about to enter the solar exclusion zone, and that demands a completely different set of assets.
Segment 2, then, addresses a fundamental obstacle in astronomy, the sun itself. As 3-IS continued its high-speed path through the inner solar system, it passed directly behind the sun, as seen from Earth.
This period is known as solar occlusion, or solar conjunction. And during this time, the intense glare and brightness of the sun just completely overwhelm any faint light coming from an object like a comet. It makes observations by ground-based telescopes or even near-Earth space assets like Hubble absolutely impossible.
So we would have been completely blind to 3-ILS.
Completely blind, yes. And during a critical phase of its journey, too, when solar heating would have been at its most intense.
This is where NASA's dedicated heliophysics missions came into play. These are assets designed primarily to study the sun, its atmosphere, and solar weather. They became the indispensable trackers.
And it's really vital to underline the historical context here. This is the first time these solar-focused missions have been purposefully mobilized to track an object originating from another solar system.
Even though they discover and observe thousands of local homegrown comets every year.
Annually, yes. This repurposing really highlights the inherent multi-purpose value that's built into these missions. They are uniquely equipped with things like chronographs and shielded cameras that can operate in the immediate vicinity of the solar disk, allowing them to pick up faint targets precisely where other assets would just be blinded.
So our primary tracking report from this phase comes from STEREO, the Solar Terrestrial Relations Observatory. It captured images between September 11th and October 2nd.
That's right. STEREO used its specialized heliocentric Imager 1, or HI-1 instrument. This is essentially a visible light imager that's designed to look at the heliosphere, the sun's vast outer atmosphere.
And initially, scientists thought the comet would be too faint to see.
They did. The initial projections were that 3I Atlas would be too faint for HI-1 to pick up, especially given all the background noise and the intense light gradients so close to the sun.
But the comet, it seems, had a surprise for them.
It did. It brightened considerably. Enough to be visible, but only through extensive data processing. And this unexpected brightening is a critical finding in and of itself.
What does that brightening suggest?
Well, it suggests that as 3I Atlas approached the sun, its volatile ices began sublimating, boiling off, faster than our models predicted. This could indicate the presence of highly reactive ices, like frozen nitrogen or oxygen.
Materials that vaporize much earlier and further out from the sun than standard water ice?
Exactly. So that detail about its composition is a key insight.
So how did they actually extract a clear image from what must have been an incredibly noisy background.
They relied on some very sophisticated image stacking techniques. They captured a continuous stream of short exposures over a long period of time. Now, in any individual frame, the comet might be completely invisible, just buried within the electronic noise of the sensor.
Right.
But because the comet is moving along a predictable path relative to the background stars and the sun, mathematical algorithms can align and combine hundreds, even thousands of these frames. And in that process, the random noise cancels itself out, and the persistent, predictable signal of the comet gets enhanced.
So they were essentially able to pull this very faint signal out of all that static.
That's a great way to think about it. And stereo's tracking during this period was crucial because it confirmed that the object was maintaining its characteristic hyperbolic velocity. It ensured our trajectory models were still sound, even during that period of solar occlusion. It was an essential continuity check.
It proved the object wasn't slowing down, it wasn't being captured, it was just passing through.
At its high interstellar speed, yes.
Okay, next up we have the PUN-NCH mission. This is the polarimeter to unify the corona and heliosphere. It's one of NASA's newest assets, just launched earlier this year.
That's right, and it provided images between September 20th and October 3rd.
And PUN-NCH gave us a tail revelation. What does that mean?
PUN-NCH provided essential context for the physical appearance of the comet while it was actively interacting with the solar environment. The mission's main job is to study the solar wind and coronal mass ejections. So they leveraged PUN-NCH's sensitivity to polarized light to get a good look at 3I Atlas.
And what specifically did PUN-NCH reveal about the comet's structure?
Its images revealed the comet's tail. It appeared as a short elongation extending away from the main body, the nucleus, and it was aligned with the solar wind, as you'd expect.
So what's significant about that?
What's significant about the PUN-NCH data is the size and the morphology, the shape of that tail. The fact that it was observed from a distance of, 231 to 235 million miles from Earth, and yet it appeared relatively short and a little diffuse, that tells us something about the dust-to-gas ratio.
And a short tail implies less dust ejection.
Precisely. Solar system comets, especially the older ones we're familiar with, they often have these long, dramatic dust tails. A short tail here suggests that the nucleus of 3I Atlas might have a low dust content, or perhaps that the material it's ejecting is primarily gas, which is much harder to see in visible light unless it's highly ionized.
So this low dust content, if that's confirmed, would be another unique compositional signature. Another way it's different from our own comets.
It would be, yes. So we're learning not just what it's made of, but how it responds to solar heating. And PUN-NCH provided that context during its most active phase.
It gave us a wider field of view and monitored that physical response to intense thermal stress right as it was rounding the sun.
That's right at that critical turning point.
Finally, in this segment, we have the ISONASA mission, USOHO, the Solar and Heliospheric Observatory. It provided confirmation data later in October.
SOHO, which has been in operation for decades now, is really the veteran of the heliophysics fleet. It tracked 3I Atlas between October 15th and 26th. It effectively took over as the object moved further away from the sun's glare relative to Earth's point of view.
And SOHO's instrumentation, particularly its wide-field coronagraphs, were able to keep tracking it.
They were. They could continue to spot the comet as a slight but distinct brightening right in the center of the image.
So SOHO's role then was really critical for confirming the continued visibility and validating the trajectory as 3I Atlas moved past its closest approach to the sun.
It closed the loop on the inner solar system passage. The collective effort of Stereo, Punch, and SOHO, it ensured we had a continuous, uninterrupted tracking record during that phase when all Earth-based observers were completely blind.
It's a stunning example of leveraging these specialized, high-reliability assets for a mission they weren't explicitly designed for.
All just to ensure that continuity of data. It was beautifully done.
So our journey now takes us even further outward. Not all of the crucial data on 3I Atlas came from those orbiters near Mars or the specialized solar trackers. NASA also maximized its resource portfolio by repurposing missions that are currently on these long outbound trajectories to entirely different targets.
These are what we call missions of opportunity.
And these distant assets, they provide a different kind of data, don't they? There's something impossible to gather from the inner solar system.
They do. When an observation is made from a great distance, the spacecraft is often viewing the object from what we call a high-phase angle.
What does that mean, a high-phase angle?
It means it's seeing the comet from the side, or even from behind, relative to the sun and the Earth. And this geometry, this different point of view, it allows scientists to study the way light scatters off the dust and gas. It gives you a much fuller, a more three-dimensional understanding of the object's structure and its activity.
So let's start with the Psyche mission. This spacecraft is currently on its way to study unique metal asteroid targets out in the main belt.
That's right. And on September 8th and 9th, Psyche acquired 4 distinct observations of 3I Ellis, and it did this over an 8-hour period.
And at the time, Psyche was about 33 million miles away from the comet.
Right, so it was providing a very early view relative to the Mars encounters we discussed.
Why was it so critical to get those 4 rapid observations in such a short window?
They were essential for what we call astrometry refinement. Because 3IS is moving so incredibly fast, its trajectory requires constant, high-precision measurement. Observing it from Psyche's remote vantage point gave us data that spanned a different arc of the sky than the observations made closer to Earth.
And that helps narrow down the uncertainties.
It helps scientists minimize the error bars on the orbital model. And that ensures that every subsequent asset, like MAVEN or Stereo, knew precisely where to point its instruments. It fine-tuned the whole operation.
And beyond just trajectory, what did Psyche reveal about the comet's physical properties?
Well, Psyche's multispectral imager provided some initial vital detail on the faint coma. That's the cloud of gas and dust sublimating off the nucleus.
And by observing the extent of that coma so early in its transit, what could scientists learn?
They could begin modeling the size and the activity level of the comet's nucleus. For instance, if the coma was larger than expected for a comet that was still so far from the sun, it would reinforce that idea we talked about earlier.
That 3I Atlas might contain those super volatile ices, the ones that boil off very easily.
Exactly. And the fact that they could integrate this observation into Psyche's cruise phase, without compromising its primary mission to the asteroid, that really speaks volumes about NASA's operational flexibility.
It shows the ability to use existing navigational instruments for impromptu science.
It's a hallmark of an advanced deep space network.
Okay, so traveling even further afield, we now look at the Lucy mission. Lucy is on its way to explore 8 different asteroids that share an orbit with Jupiter. These are known as the Trojans.
And Lucy provided its observation data on September 16th. It took images from a truly staggering distance, 240 million miles away from 3I Atlas.
240 million miles. That had to be the furthest out observation point during this whole core phase of the campaign.
It was, yes.
Which instrument did they leverage for a shot that distant?
Lucy used its LORRI panchromatic imager. Now, LORRI is optimized for high-resolution black and white imaging of distant, faint targets, which made it absolutely ideal for this kind of spontaneous astronomical task.
And given that distance, I assume they had to use that image stacking technique again.
They did. It was crucial for pulling that very faint signal out of all the background noise.
So what specific details could LORRI actually capture from 240 million miles away?
The stacked images provided excellent detail on the comet's overall morphology. They captured the fuzzy halo of the coma and the short tail, which appeared as a sort of smudge of gas flowing off to the right.
But the real value came from that high phase angle you mentioned.
Critically, yes. Because Lucy was viewing 3I Atlas from a significantly different perspective than Earth or Mars, the data helped characterize the scattering properties of the dust and the gas.
How does that different viewing angle help us interpret the composition?
Well, the way that light reflects off dust depends heavily on the angle between the sun, the object you're looking at, and the observer. So by comparing the brightness and the polarization of the coma as seen by Lucy at its unique phase angle versus the brightness seen by the Mars assets, scientists can start to infer the physical properties of the dust grains themselves.
Their size, their shape.
Even their porosity. If the grains scatter light differently than the dust from our own solar system comets, it further reinforces the idea that this interstellar visitor has a unique composition.
So that structural data is just as vital as the chemical data.
Absolutely.
And you mentioned the image spanned about 11 arc minutes of the sky. Just to help us visualize that scale again for our listeners, that's about 1/3 the apparent width of the full moon.
That's right. So imaging a faint object that spans 1/3 of the moon's apparent width from 240 million miles away, it just underscores both the enormous scale of the comet's activity, its coma was vast, and the technical precision of that LORRI instrument.
So these 2 deep space interceptions from Psyche and Lucy, they were crucial for providing the 3-dimensional structure and the high-angle context that the inner solar system trackers just couldn't achieve.
A truly impressive utilization of resources that were already in transit heading across the solar system.
As 3I Atlas passed through the inner solar system, its characteristics were changing, well, minute by minute because of that intense solar radiation. To capture the full scope of these dynamic shifts, NASA had to mobilize its most powerful assets, its flagships.
This is where we get the high-powered view. The focus here was on obtaining complete multispectral coverage.
This is where the flagship space telescopes enter the campaign. They provide the ultimate gold standard in high-resolution, multi-wavelength data.
Right. Shortly after the comet's discovery back in early July, the veteran Hubble Space Telescope viewed the object later that same month.
And then, in August, the deepest eyes in the sky joined the effort, the James Webb Space Telescope.
And SPHEREX, the spectrophotometer for the history of the universe, epoch of reionization, and ICES explorer.
So the combined power of these three telescopes, it's designed to capture the entire electromagnetic fingerprint of 3I Atlas.
That's the goal, moving from visible light through the ultraviolet and deep into the infrared. Each wavelength band reveals different chemical and physical truths about the object.
Let's start with Hubble. It operates largely in the visible and ultraviolet ranges. What specific structural information was Hubble providing that the other assets couldn't?
Hubble gave us crucial data on the morphology and the activity rate of the dust. By capturing the comet in UV, scientists were able to measure the production rate of specific atomic species, things like oxygen and hydroxyl radicals.
Which are direct indicators of sublimated water ice.
Exactly. But more importantly, Hubble's superior resolution allowed for fine structural details. It could track the development of faint jets or shells within the coma, and it could precisely measure the speed and direction of dust ejection over time. This visible and UV data is necessary to understand how the surface is actually reacting to the sun.
And then, of course, there is the James Webb Space Telescope. Given its specialization in the infrared spectrum, Webb was, you could argue, the most critical asset for determining the actual composition of 3I Atlas.
It was certainly a centerpiece of the campaign. Webb's infrared capabilities are peerless when it comes to molecular identification.
So what specific compounds was Webb uniquely positioned to search for?
Scientists used Webb to search for the specific fingerprints of complex organic molecules and exotic ices that would really confirm an extrasolar origin. They targeted signatures of methane, ammonia, hydrogen cyanide, and perhaps even more complex hydrocarbons.
Why are those specific molecules so important for an interstellar object like this?
Well, if 3I Atlas contains a high proportion of these highly volatile ices, especially molecules like methane or carbon monoxide that sublimate so easily, it strongly indicates that the comet formed in the extremely cold outer regions of its native protoplanetary disk.
Perhaps even further out than the Oort cloud of our own system.
That's the idea. And furthermore, finding certain crystalline structures in the silicate dust or complex carbon chains, that would provide a direct comparison to the raw materials we find in our own solar system. And that comparison has immense implications for, the prevalence of life-enabling chemistry across the galaxy.
And finally, rounding out this trio, we have the specialized capability of SPHEREX. As its name suggests, it's designed to explore the spectral fingerprint of the universe. What role did it play in August?
SPHEREX really complements Webb. It provides a wide-field, low-resolution spectral survey across a very broad swath of the infrared. So while Webb provides that high-resolution detail on a very narrow field of view, SPHEREX helps map the overall distribution of various ice and dust components across the entire object.
It's searching for unique chemical signatures and spectral features.
Right. Things that might reveal materials, perhaps unique silicates or crystalline compositions that are simply not present in the cometary materials we typically find orbiting our sun. By combining SPHEREX's wide survey data with Webb's targeted high-resolution results, scientists can build a complete inventory of both the volatile and the refractory components of 3I Atlas.
So by combining data from these three flagship telescopes with the detailed chemical analysis from its CFEN and the structural insights from the deep space probes, scientists are constructing this exhaustive, multidimensional profile of 3I Atlas.
And that's the ultimate scientific payoff. This comparison to the thousands of homegrown comets we already have data for. The full spectrum coverage ensures that nothing is missed. No exotic ice, no unique silicate, no unexpected organic molecule. It is the key to finally answering that question. Is the recipe for planetary formation universal, or is our local environment unique?
Let's look now at the final trajectory report. The object is still speeding through our system. When will it make its closest approach to Earth, and when will it finally leave our observation zone?
The comet's closest approach to Earth is scheduled for Friday, December 19th of this year, 2025.
And just to address any public concern, what is the distance of that flyby? We should be very clear about that.
Absolutely. It will pass us at a distance of 170 million miles. That is nearly twice the distance between the Earth and the Sun. It is a purely observational event. It poses absolutely no threat, but it does provide a final, excellent viewing opportunity for our far-ranging telescopes.
But the observation campaign won't stop in December.
No, that's correct. NASA spacecraft will continue to observe 3I Atlas until it finally passes the orbit of Jupiter and truly begins to recede into the outer solar system. We'll be tracking it specifically until the spring of 2026.
Why is that extended tracking phase so essential?
Because it allows scientists to measure the object's decay in activity. How quickly does the emission of gas and the size of its coma diminish as it moves away from the sun's heat? This off-ramp data provides a final inverse look at the volatility of its materials.
This entire systemic observation effort, the coordination, the repurposing, the execution by a dozen assets, it really has to be seen within the broader context of NASA's operational environment.
That is the essential takeaway for operational capability. It was only possible because the agency maintains this vast and diverse portfolio of missions. The search for knowledge across the solar system is driven by these parallel overlapping efforts.
Right, so the compositional analysis we get from 3I Atlas, it directly informs and contrasts with data gathered from other missions focused on origins in life.
For instance, the findings from Webb regarding complex organic molecules on 3I Atlas will connect directly to the recent Cassini study that found organics fresh from the ocean of Enceladus.
That's a perfect example. Cassini was focused on the organic building blocks coming from the subsurface ocean of one of Saturn's moons. It was looking inward to find the ingredients for life in our own system.
And 3I Atlas provides the necessary external reference point. It allows us to ask, are the organic molecules in this interstellar comet similar to those being created right here in our own system, or are they uniquely different? It establishes a vital scientific dichotomy.
And similarly, the deep space context from 3I Atlas's trajectory ties into things like the Webb observation of the dust shells spiraling around APEP, a massive stellar system far outside our own.
Yes, the SphereX and Webb data on this comet's dust and crystalline structure, it provides a tangible sample of matter forged elsewhere. And this sample can then be compared to the spectroscopic data we collect on other star formation environments, like APEP, helping us understand the evolution and ejection mechanisms within stellar systems across the entire galaxy.
And we should acknowledge that all of this sophisticated astronomical observation was conducted while NASA was simultaneously continuing crucial operations across the board,
Oh, absolutely.
including the launch of the Sentinel-6B Earth satellite focused on oceanography and the successful completion of flight tests for the experimental X-59 quiet supersonic aircraft.
The sheer operational volume from Earth science and aeronautics to human spaceflight support via the International Space Station, all of it running in parallel to this high-tempo astronomical interception, that is what enabled the success of the 3I Atlas campaign. It wasn't a dedicated mission. It was a systemic priority that leveraged an existing, robust, and highly coordinated infrastructure.
So we have tracked 3I Atlas from its very first sighting to its most recent high-powered examination. The defining success of this unprecedented campaign is clear: gathering detailed, multispectral data from a dozen strategically positioned assets across the solar system.
And that's a level of coordinated analysis that was simply unattainable during the transits of the first two interstellar objects we detected.
This exhaustive data set now allows scientists to perform the ultimate scientific comparison, placing the complete chemical and physical profile of 3I Atlas right next to the known profiles of thousands of our own solar system comets.
We now hold a wealth of visual, chemical, and spectral information to unlock the secrets of its birth star system.
And this data, it immediately feeds into some of the most profound questions that are driving human space exploration. What does this unique interstellar sample mean for humanity's understanding of our cosmic origins? The analysis of 3I Atlas's exact chemical makeup will directly inform the search for life in the universe.
It will. I mean, if the raw materials carried by 3I Atlas, the volatile ices, the complex organics, if they were found to be chemically similar to the materials we find right here in our own system, it significantly increases the probability that the chemical pathway to life is common throughout the galaxy.
And if they're different?
If, conversely, the materials are wildly different, it suggests that our solar system may possess a unique chemical inventory, and that would make Earth potentially much, much rarer.
So the study of 3I Atlas provides empirical, tangible evidence from outside our solar system. It moves us beyond relying solely on theoretical models of exoplanetary formation.
And the final implication of this historic systemic observation effort is really the most profound. This data will eventually reveal whether the raw materials used to form planetary systems far away in the star system that ejected 3I Atlas are fundamentally similar or profoundly different from the essential ingredients that formed our Sun, Mercury, Venus, Earth, and Mars.
Are we constructed from universal cosmic building blocks? Or are the ingredients that built our home truly unique in the wider galactic neighborhood? That is the ultimate question that scientists are now beginning to address as they sift through this mountain of data collected during 3I Atlas's transit.
And the observation campaign continues through the spring of 2026. We will be eagerly awaiting the initial compositional findings once all the data processing is complete. That will mark the next phase of this interstellar discovery.
For now, the Interstellar Comet 3I Atlas is speeding out of view, leaving behind a profound legacy of scientific collaboration and a definitive high-resolution sample from another star. We hope you feel thoroughly informed about this extraordinary deep dive into our solar system's latest and fastest visitor.